be starting with the next chapter today, which is work, power, and energy. Um, I will keep aside some time in either today or tomorrow's lecture for any remaining doubts in friction. So please continue with the questions from friction and Newton's laws of motion. First of all, if anything pending in HC Verma, finish that, and also the questions from the module. So over this week and next week, we will keep aside some more time for questions and doubts from friction. But we will be starting with a new chapter with work by energy today. So this is a continuation of the mechanics section of class 11th and very essential chapter. Okay. So work by energy is like an alternative approach to solving mechanical problems, alternative to Newton's laws of motion, where in Newton's laws of motion, we are relating the dynamics of a system with vector quantities, force, then from force, the net force, and from net force, the calculation of acceleration or rate of change of momentum. So we are dealing with all vector quantities like force, acceleration, momentum, etc. Whereas in this chapter, we will see that the essential application will be of something called work energy theorem, where we'll be relating work and different types of energy like kinetic energy and potential energy. And as you know, these are all scalar quantities. Work is also a scalar quantity. Energy is also a scalar quantity. So the application of work energy theorem will ultimately involve a scalar application or the calculation of scalar quantities for how a dynamical system progresses. So in that sense, it is an alternative description of the dynamics of a system, alternative to Newton's laws of motion. Okay. So let's start by understanding the definition of the quantity work done. Then as we progress, we will understand how work is related with energy of a system, energy being the mechanical energy, which in turn is the combination of kinetic energy and potential energy, and the relationship between these quantities, the work done by the forces, the various different types of forces on a system and what work they're doing with respect to the various different type of energy of a system like potential energy and kinetic energy. So that is essentially what the chapter is about. So let's start with the first definition and the absolute basic, which is work done. Work or work done by a force. So again, this definition or this particular quantity we will be seeing in different type of situations. Okay, so the first and most simple situation in which we'll see the definition of work done by force is the situation where if the force we are talking about is a constant force. Okay, so work done by a constant force. And by constant, we mean constant in both magnitude and direction. So for a force which is constant in magnitude and direction, the work done is simply defined by the mathematical equation F dot S, or it is the scalar product of force with displacement. Okay, where S is the displacement of the particle on which the force F is applied, or in case of F acting on a body, then S is the displacement of the point at which force acts. Or this is often called the point of application. So just write down the definition. We'll understand the difference between the displacement of point of application and displacement of a particle. We'll understand with some examples. Just write down the definition. Okay, so let us understand a couple of aspects about work done. Or so as you can see, W, or the work done, is a scalar quantity. Secondly, the SI unit of work is joules, where 1 joule equals to 1 Newton meter, which is the same thing as 1 kilogram meter square per second square. CGS unit of work is given a name of erg, where 1 erg is equal to 1 dyne centimeter. Now that is the same thing as 1 gram centimeter square per second square. You can also see the conversion that 1 erg equals to 10 raised power minus 7 joules. So this is simply about the units. Now let's come back to the point of the displacement in the definition, S being the displacement of the point of application. The force. So for example, for a force acting on a particle, let's talk about that. Like suppose a particle displaces from here to here. This is the displacement of a particle on which a particular force is acting. Now it may be that the particle's actual path is this. Doesn't matter. The actual path might be this, but it is moving from this initial position A to this final position B. Okay, so for a force F acting on a particle P displaced from, let's say, A to B. So the displacement is vector S. Okay. So you can see that the point of application of the force F is the particle P itself. Therefore, the displacement of the particle is the same thing as the displacement of the point of application. So in the case of a particle on which a force is being applied, the definition of S becomes very simple. It is just the displacement of the particle itself. Okay. But when the force is acting on a rigid body, the situation might be a little bit more complicated, which we'll come to in the next example. Yeah, Kanishk, I'll take you back to the CGS unit, but first just note down this part. CGS unit was erg, so we'll come back to that. Just note down this example and this section first. Yeah, Sarah, so see what is happening now. If the force is acting on a particle which is moving from the point A to B, then whatever the displacement of the particle is, same is the displacement of the point of application of the force, because the particle is a point mass ना. So force का जो point of application है वो क्या है, वो particle का ही point mass है ना. So they are one and the same thing. You understanding? The difference will come when we see the situation of a rigid body. I'm coming to that next. Okay. The difference between the two things, that what is the displacement of the body versus what is the displacement of the point of application, that can come in a situation where instead of the force acting on a particle is acting on a rigid body, or for that matter it's acting on a body. It can be a non-rigid body also, like an elastic body also. I'll come to that. Okay. Okay, so I'm just taking you back to the section about the CGS unit. So CGS system, as you know, is centimeter gram second system, whereas SI is the standard international system of units. So in CGS system, the unit of work is called ERG, ERG. The name is ERG. Okay. Where one ERG becomes the work done by one dyne of force through a displacement of 1 centimeter along the direction of the force. So accordingly, one erg is equal to 10 raised power minus 7 joules. Because as you know, one dyne of force is 10 raised power minus 5 joules, sorry, newtons. Okay. And obviously 1 centimeter, you know, is 1/100th or 10 raised power minus 2 of a meter. So that's why this quantity becomes this. Okay. Now coming back to displacement of the point of application. Now next let us see force F acting on a rigid body, okay, displaced through S, such that the body is in translation. In kinematics, you would have heard the term translation or linear motion versus the concept of rotation, which we'll come to later. So, for example, let's say we have a situation where a block is being pushed by a force like this, let's say, and under the action of the force, the block makes a displacement like this from the point A to the point B, or from the position A to B. So force F acts on the block while it moves from position A to B. Okay. So now in this case, you can see that if I make a more detailed diagram, this point at which we are applying the force now on the body, this is the point of application. P is the point of application of the force F. And we will define the work done by F as F dot S, where S is the displacement of that point. Okay. So in this case, you will see the displacement of that point is nothing but the displacement of the rigid body. So in this case, the point at which we are applying the force, as the body is moving from position A to position B, that point itself is displacing by the same amount by which you can say the entire body is displacing. This is the displacement of the point of application where we are applying the force. So again, this is the same as the displacement of the block. Now this is because, why it's exactly the same? Because the block is in linear motion or translation. Okay. And actually in this particular chapter, whenever we are dealing with, the application of work done concept, it will always be in a situation where the body we are considering is in linear motion. But in future chapters, okay, future chapters like rotational mechanics, then later in elasticity, we will see that that is not always the case. Okay, so I'll take you to an example next like that. It's not always the case that a rigid body or a block in this case is in translation or linear motion. And it's not always the case that the displacement of the point of application of the force will be the same as the displacement of the body, therefore. Okay, so I'll show you in an example next that if the body is not in translation but in rotation, then the two quantities will become different. The displacement of point of application versus the displacement of the body. Okay, they can become different things. But make a note of this example first. Okay, so as far as our applications of work done in numerical problems in this chapter will come, actually, we'll always be dealing with this kind of situation where the body in concern is going to be in translation. So the displacement of the point of application will always be the same as the displacement of the body or the block itself. Okay. However, for future chapters, you should be aware that in case the body is in rotational motion, or it is in a situation where it's not a rigid body, the situation can become such that point of application is different from the center of mass of the body's displacement. Okay, the displacement of point of application can become different. So next, let's look at an example where F is applied on a rigid body in rotational motion. Instead of translational motion, it is in rotational motion. So for that, I'll take a simple example of a situation like this, that we have a rod. So our rigid body is like a rod like this, okay, and that rod is pinned, or it is what we call hinged, like this. So this is a rod which is hinged such that it can rotate freely, okay, such that it can rotate freely about the hinge. Now in such a case, suppose we are now applying a force, and we apply the force at the far end of the rod, like this over here. So F is a constant force which is acting at the far end, acting at the end P. So the point of application of the force is this end point P on the rod. Okay. So now what will happen is, as a result of the application of this force, instead of the rod moving like this, instead of this happening, this is not going to happen. Instead, what is going to happen? The rod is going to rotate about this, like this. Okay. So even as you are applying the force, the rod will be in this sort of motion. So if after some time the rod reaches this situation now, so you can see that the displacement of the point of application that we'll have to consider will be this displacement. So as the rod goes from the initial position to the final position here, we will have to calculate the work done by this force as F dot S, where S will be the displacement of P, which is the point of application of the force F. Okay, and mind you, that is not the same thing as the point of, I mean, the displacement of the center of mass. The center of mass of the rod will be here. So the center of mass will have a different displacement. You can see the displacement of the center of mass will become this vector here, which is different from the displacement of the point of application. This will be the displacement of the center of mass. So you can see that this is a situation where the body center of mass is having a different displacement compared to the displacement of the point of application. It's not the same thing as the displacement of the center of mass. So in a future chapter like rotational mechanics, when you study this kind of situation, you have to have the clarity that in this case, if this force is a constant force acting at this point continuously, while this point is displaced via this circular path from here to here, the the work done by the force will be given by this formula, where S is the displacement of the point of application of the force, and it is not the same thing as the displacement as the center of mass. So hope this point is now clear, Sarah. It's clear that what is the difference between displacement of point of application and displacement of center of mass. Okay, good. Okay. Another situation in which there is a difference between the displacement of the center of mass and the displacement of the point of application. Okay. Okay. So another situation where the two things will become different is in a situation where the body on which the force is applying is applied is not a rigid body. It is a elastic kind of material. The force, which is it's a constant force acting on a body of elastic material. For example, suppose I have this situation now that I have a solid rubber block like an eraser that you use. This is a rubber block, and I have kept this rubber block at the corner between a smooth floor and a vertical wall. So I placed it like this. Now I start applying a constant force at this point over here. And as a result of the application of the force at the point P, the block now gets compressed after a while. So the point of application of the force is displacing again in a different way compared to the center of mass. This point of application of the force, this is making a displacement like this. This is that displacement. Whereas the center of mass of the body, that is making a different displacement. The center of mass of the body is now reached somewhere here. So you can see that it's a different displacement. It's lesser. So you can see that again S is not the same thing as the displacement of the center of mass, because in this case we are dealing with an elastic material which is changing shape. So because that is happening, this is the case. So we will encounter situations like this in a chapter called elasticity and properties of matter at a later stage when we discuss about this elasticity and properties of matter. In that we will encounter these kind of situations. Okay, so hope these examples are clear. And through this, in terms of definition, you are clear that when we are talking about work done by a constant force, always, whether it is like an elastic body undergoing a shape change, or it is a rigid body in rotational motion, or it is the simple case of a rigid body in translation, like the first case we had seen, the general definition of the quantity S is it is the displacement of the point of application. where we, of course, we understand that in the case of translation of a rigid body, okay, for translation of a rigid body, this S also becomes, is the same thing as the displacement of the body itself, or center of mass of the body. But in other cases, it may not be the same thing, like I showed you with those examples. So now let's look at a typical example and see the implementation of this formula in calculation of work done. So let's look at a typical mechanical situation like this, where we have, let's say, a rough inclined plane. Angle of inclination 37 degrees. Okay. Now in this, let's say we are looking at a block sliding down the inclined plane through a certain amount of displacement. Okay. So we have a block. Now this has a coefficient of friction of 0.5. And the block slides down from the position A to B. So show all forces acting on the block in a free body diagram. So the block slides from A to B, which is a distance of 10 meters, let's say. Okay. And then we have to calculate the work done by each of the forces. Okay. Take acceleration due to gravity, obviously, to be 10 meters per second square. Okay, now just work out this question quickly. You have to just apply this formula to each of these forces, because they're all constant forces, you will see, acting on, and it's a case of a body which is in translation. It's going in linear motion from A to B. So there's no complication about what S is. And S, which is the displacement of the point of application of force, is the same as the displacement of the whole body, or the center of mass of the body. Okay, so what are the answers? You know that the number of forces acting on this are three forces. There will be weight, mg, normal reaction, n, and friction, kinetic friction to be precise. Okay, so you have to calculate the work done by each of these. How much is the work done by mg? How much is the work done by the normal reaction? And how much is the work done by the friction as the body is displacing from A to B? So let's look at this. So concept of free body diagram is still quite essential in a situation like this, even though we are not directly solving Newton's laws, but so let's show all the force vectors. Mg is acting vertically downwards. Okay. Normal reaction is acting in this sort of direction, and friction is acting in this sort of direction. This is kinetic friction equal to mu n. The normal reaction is acting along this perpendicular direction. This is mg. So remember the mass was 2.5 kg and the angle theta was 37 degrees. So we have, this is 25 newtons. Okay. We have normal reaction will balance the cos component of mg. So in this case, that will become 20 newtons, and kinetic friction will be equal to mu n. So in this case, that will become 10 newtons because the coefficient of friction was 0.5. Okay. Now, and of course, you know that this angle here is also theta. So now as the body goes from here to here, the displacement of the point of application of all these three forces is the same as the displacement of the body itself, or the center of mass of the body. And that we have taken as how much? As 10 meters. So you can see that this angle here is 53 degrees. Okay. So the work done by mg will be this gravitational force's dot product with displacement. So that will become mgs cos 53, or the same thing as sine 37. So 25 multiplied by 10 multiplied by 3 by 5. So that will be 150 joules. This is the work done by mg. Now similarly, calculate the work done by normal reaction and calculate the work done by friction. So work these out and tell me how much they are. Right. So let's look at it. Tantresh and Anmol, just verify the answers. So yeah, normal reaction, you can see the work done is zero, because it's perpendicular to the displacement, because n is perpendicular to the displacement. So whenever a force is perpendicular to displacement, you can see n is like this, and the displacement vector is like this. So the force is acting perpendicular to the displacement. But in the same diagram, you can see friction is at 180 degrees. So the work done by friction will be minus of the magnitude of friction, because theta is equal to 180 degrees for friction with respect to the displacement. So as you can see, friction is 10 newtons in magnitude, displacement is 10 newtons. So this will become minus 100 joules. Okay, so hope the calculation is clear to all of you. Work done by normal reaction is zero. Work done by friction is negative of 100 joules, and the work done by mg is positive of 150 joules. Okay. So this is how we calculate the work done by constant forces. Now next we will see, what if a force is changing while the body is moving, or we have what is called a variable force. Then how do we calculate work done in that case? Okay. So coming back to definition of work done by a variable force. So by variable we mean that the force F is changing. That is either its magnitude or its direction, okay, or both magnitude and direction is or are changing during the displacement of its point of application. We'll look at physical examples of this also, but in such a case, the work done by the force is given by a more complex definition, and that work done is given by the definition that it is integration of F dot ds from initial position to the final position. So this is called the path integration of forces scalar product with differential displacement. So here ds is what we call a differential displacement, or it is the displacement in a very small interval of time dt. And f is the instantaneous value of force, because the force is changing from time to time. So it is at that instant of time dt, whatever the value of force, that instantaneous value is given by the vector f. So note down this definition, and once again we'll understand its application with examples. Okay, so let's look at very common example. The work done by a spring force. You know that spring force varies according to the formula kx, opposite x in direction. So suppose we have this situation where we have attached a block with a spring against a rigid wall, and starting from a position where the spring is in natural length, we are now pulling the block using an external force in such a way that the spring extends by a certain amount. So let's say in this diagram, the spring is in its natural length, L. But now we start pulling this block with some force. And as a result of that force, eventually what happens is that the block moves to some position like this. So let's say the block has got displaced by D like this. So given that suppose the spring constant is 100 newtons per centimeter, we want to find the work done by the spring force acting on the block, okay, as the block moves through, let us say, a distance of 5 centimeters. So you want to calculate this, okay. So here, notice what will happen is that the spring force, this will be a variable force. So work done we'll have to calculate by integration method, by path integration method. Instead of dot product of F with S, we'll have to integrate dot product of F with ds. But here in this case, what we're talking about is we are talking about the work done by the spring force. So we'll have to integrate the spring force with respect to the displacement along the path. Okay. So we'll come to this, just make a note of the question statement first. Okay, so now let's understand this question. So because the spring force is variable, now we cannot directly calculate work done as spring force dot product with displacement. So what we have to consider is that some intermediate time, suppose this was t equal to 0 and this is at some later time capital T. Now in between, in between t equal to 0 to t equal to capital T, at some instant, Suppose this was the situation that the spring is stretched by x. So x is less than the total displacement right now. So the spring force that is acting on the body, that will have a magnitude of kx and direction like this. So now for a differential displacement of dx in this direction, the work done by the spring force. So at this point of time, for a differential displacement of dx in some very small time dt, the work done by the spring force will become this. So this will become minus of kx dx, okay? Because you can see that the spring force has a magnitude of kx, okay, and acts at theta equal to 180 degrees with respect to the displacement ds. The magnitude of that displacement is dx, but this acts at 180 degrees with respect to the displacement. So this becomes minus kx dx like this. So the total work done by the spring force from t equal to 0 to t equal to capital T, when x was 0 to x equal to cap T. The above diagram, you can see that going from a situation where the spring was at natural length to a situation where the spring is now extended by d. So your extension of the spring was 0 here, and the extension of the spring is d over here. So that total work done is going to be integration of this, which will further become from initial to final. So that will become integration of minus kx dx from equal to 0 to x equal to d. So this will become. So in this case, the work done by the spring force will be minus of k, which was how much was the spring constant? This much, or in SI unit it was this. In SI unit, this is this. Just substitute the values. So this becomes the calculation of work done. So make a note of this example properly, please, and make sure you have understood how we have carried out the integration, the path integration of force over displacement. In this case, the spring force over displacement, when it's integrated, it is minus kx dx integration. Okay, so hope this example is clear to all of you. Let's do another numerical example for work done by variable force. So this time what happens is a particle is moving along the x-axis, okay, under the action of a variable force F equals to okay, where K is a constant of, let us say, 50 Newton meters square, and X is the X coordinate of the particle. So calculate the work done by this force for a displacement from x equal to 2 meters to x equal to 4 meters. Just work this out quickly, people. All right, so let's check out the answer. Tantresh, we have got 12.5 joules. So let's understand this. So let's say when the particle is somewhere on the x-axis, so its instantaneous location is here at x equal to x. So the force acting on the particle at this instant will be like this. It will be along the positive x-axis, but it will have a variable magnitude. The instantaneous magnitude of the force along the x-axis is k by x square. Okay. So now, if it makes a small displacement along this direction, so you can see that the differential work done by that force, it will just become f dx or k by x square dx. So now if the particle is going from this position A, let's say, where x was equal to 2, to this position B, where x has become 4, the work done will become this quantity. So it will become k by x square dx, integrated from x equal to 2 to x equal to 4. Now you know that integration of dx by x square is this, so it is. So now this you have to put the limits. Okay, so this becomes the work done. Okay, so hope this example is clear to all of you. Okay, now let's look at slightly different situation in which we'll be applying this work done by variable force concept. So in our next example, we have let us say So this is a smooth hemispherical surface. Of radius 20 meters. Okay. Now, let's say a particle was initially located at this position, which I'm showing here. So particle P is initially at this position, say the point A, and this lower point here is the point B. So initially it was at this position where this angle is 60 degrees. Okay. So a particle P of mass 2.5 kg slides down from position A to B. So calculate the work done by each of the forces acting on it. Again, take acceleration due to gravity to be 10 meters per second square. So now in this example, what we'll see is there are two forces acting on the particle at any point of time. One is the gravitational force mg and the other is the normal reaction force n. Okay. But the difference is this time gravity will be a constant force, okay, whereas normal reaction will be a variable force. So when the particle is at any intermediate position like this, okay, so this is where it started from at time t equal to 0, and this is where it will eventually reach at some time t. But at some intermediate time, let's say the particle is located at some position like this at some time t. So it makes a differential displacement in which direction? Along the tangent to the circular path. So this is the differential displacement. Okay. And the forces acting on it will be the weight mg and the normal reaction n. So as you can see, the normal reaction will act in such a way that it is always perpendicular to the displacement. So at any position of the particle, normal reaction acts perpendicular to the differential displacement ds, because ds will be tangential or along the tangent, and normal reaction will be radial, okay, pointing to the center of that hemispherical path. This is C, the center of the hemisphere. The normal reaction at any point will be pointing towards that. Okay. So what will happen is, even though n is a variable force, so n is going to be equal to, it's going to be a variable force. Doesn't matter how much it is equal to. So work done by normal reaction will become 0 because it is perpendicular. So because of this now, at any point from A to B. Okay. So the total work done by the normal reaction will be 0. Okay. Whereas as you might have guessed, when it comes to the other force, the work done by mg, we don't have to use integration. Work done by mg, that is a constant force. Okay. So we can write it as a vector as minus mg j cap, taking this as our xy. So the work done by mg will just be mg dot s. Okay. So when you do that mg dot s, you will see that from A to B, the displacement vector from the point A to the point B will be how much now? Now that we can easily calculate by using this geometry. This angle is 60 degrees. So going along this circular path. So we can see that the magnitude of the displacement will also be r. Okay. And the angle it will be making will be such that you can see that this angle is 60 degrees. So this angle will be 60 degrees. It will become an equilateral triangle. So mg is acting vertically downwards. You can see the magnitude of the displacement will be equal to r, and theta will be 60 degrees with respect to the vertical. That is just the geometry of this. Just so happens that when we take an arc which is subtending 60 degrees, this makes an equilateral triangle. That's why this becomes r. And this angle becomes also 60 degrees. So you can see here the work done by mg will be mass of the particle was 2.5 kg, okay, and g we are taking as 10, and the radius was 20 meters. Into cos 60, which is half. 25 into 10, so 250 joules. This will become the work done by gravity, whereas the work done by the normal reaction is 0. So this becomes the final solution to this question. Okay. So hope this is clear, people. Make a note of this, and that's the conclusion of today's session. So tomorrow's lecture, we will look at more examples of calculation of work done by variable force, but most importantly, we will look at the relationship between work done and kinetic energy. Okay. and through that a theorem called work kinetic energy theorem. And tomorrow in the second half of the lecture, we'll also keep some time for discussion of any doubts and questions from friction. So please, as I said, continue working on problems from friction from your module, as well as if anything is pending from HC Verma, and keep the doubts ready. Tomorrow we will discuss. Okay, that's it for today's class, people. Wish you all the best.